In this video, I'm going to talk about functions for playback, adaptive tuning, and analysis in Zen. But first, I'm going to introduce the function random. Random, with no arguments, just creates one random number between 0 and 1. I can also make random generate a list of random numbers. So here I want a list which is 6 random numbers long. These are all between 0 and 1 again. So let's say I want these to be frequencies in the range of 200 Hertz to 700 Hertz. So I just have to multiply by 500 and add 200 to this range. So now I have a bunch of random numbers between 200 and 700 Hertz. And so with these, I can actually play these back. And I pass them to the function play, which will interpret them as frequencies. And if I wanted, I could actually play these back with a different sound. So there are these things which are called wave shapes, which are just little words like triangle or try. Either one works. If you pass them as arguments to play, it'll change the sound. And it actually doesn't matter where I put them. I can put them in front or behind or wherever. The order of the arguments doesn't actually matter for play. And there's also sawtooth, there's sine, and there's square. Anyway, I didn't really enjoy listening to these frequencies very much. So what I want to do with these frequencies is I actually want to justly tune them. So what I'm going to do is I'm going to use this function approx partials, which will take these frequencies and it'll try to compare them with the harmonic series and determine what the fundamental is and which partials they are. So here it took these random frequencies between 200 and 700 Hertz, and it said that, okay, 300 is probably the fundamental, and then the first one you gave me is very close to the 16th harmonic of this fundamental. The second you gave me is very close to the 20th, and so on. It's designed in a way so that the results you get, that is these retuned versions, will all be within 50 cents of the original. So because the function play is very flexible, we can actually pass in this answer, which is a list of two things. So this answer is a list of one frequency and then another list of ratios. So we can actually pass in this answer and it'll play it back for us. So this is like a justly tuned version of 6 random numbers between 200 and 700 Hertz. We can also get a version of this answer that's expressed in a way we can read better. If I just use the function just with the same arguments, it'll generate a list of numbers, which are the approximated versions of the arguments I gave it. So these are all the frequencies that have been adjusted. To show you what I mean, let's say we have a variable x, which is this list of random numbers. If we show x, it looks like this, but if we justly tune x, there'll be a bunch of numbers that are pretty close but not exact because they've been rounded off to take the place of partials in the harmonic series. So let's say we wanted to design a piece where we want to use the frequency ratio of pi, which is 3.14, and e, Euler's number. So pi to e is our ratio. And when I create this ratio, Zen will actually try to create a integer ratio that approximates it very well. So if we look at how many cents this integer ratio is, and then how many cents the actual interval pi to e is, they're going to be exactly the same. And so if I give an interval as an argument to play, it'll play it back with the bottom note being 261.63 Hertz, which is middle C. I can also play back this interval at other transpositions, such as if I wanted to play it back starting at MIDI note 69, which is 440 Hertz. So anyway, we're pretending that we're creating this piece using this interval pi to e. And so because we want to make it easier to put together this piece, we're going to choose some equal temperaments that really well approximate this interval. And there's a function to do that, actually. So if I have this interval, which is pi to e, so if I give this function closest a ratio as the argument, it'll give me a bunch of nearby equal tempered intervals. So if we look at the size of these intervals, they're actually very close to pi to e. So this means that maybe if I was designing this piece, I want to have part of the piece in 24-tone equal temperament, part of the piece in 43-tone equal temperament, and maybe part of the piece in 19-tone equal temperament. And if I wanted more, I can actually provide another argument to closest. Let's say I want 10 of these. So these are all like 10 very close equal tempered values that approximate this interval. So that's what happens when you give closest a ratio as its first argument. If I give closest an equal tempered value or a cent value, let's say I have the equal tempered version of this, which is going to be the same thing but in a different data type. If I give that as the first argument to closest, it will actually find the closest ratios that best approximate it. So this in here is still a certain size in cents or in 12-tone equal temperament. But here I'm finding the closest ratios to it. And these guys aren't actually that close, which isn't great for me because I actually want them all to be within 1 cent. And so what I can do is pass in another argument to closest where I specify how far away these ratios can be at the most. So now these ones are actually super close to my around 250 cents I was looking for. And just like before, I can ask for more than 5 of them. I can ask for 10. And so I've found a bunch of rational approximations for pi over e, and they're all expressed as ratio values. So I've shown what happens when we give closest as its first argument a ratio. We get a bunch of ET intervals that approximate it very well. And when we give it an ET value as its first argument, we get a bunch of ratios that approximate it. If we give closest a list of intervals, actually a list of ratios as its first argument, let's say 5 to 4, 3 to 2, and 7 to 4. If we give this list as the first argument, we'll actually get a list of equal divisions of the octave that can best represent all these intervals. And just like before, I can ask for more than 5 of them. I can ask for 10 of them. And so if I wanted to find out how to play these intervals in, let's say, 53-tone equal temperament, I can just put them in a list and then use this hash operator to convert them all to 53-tone equal temperament. So that means that 17 steps in 53-tone equal temperament is very close to 5 to 4, 31 is very close to 3 to 2, actually it's pretty much exact, and 43 is very close to 7 to 4. The last function I'll show is called simplify, and what simplify does is it takes in any sort of node or ratio. It'll convert it to a nearby ratio with a low denominator. So 4 steps in 12-tone equal temperament is approximately equal to the 29 to 23 ratio. If I check that out in cents, it's 401 cents. Let's say I didn't want to go all the way up to 29 limit. I can actually put in this answer again and simplify it even more. Now I have 24 to 19. So that in cents is a bit farther away. And then I can further simplify this answer. And now it's 5 to 4, which of course is now 14 cents away from 400 cents, which is our target. Which means that these are all good approximations of 4 steps in 12-tone equal temperament, but they're getting simpler in the denominator every time. If I wanted to see all these ratios that approximate 4 steps in 12-tone equal temperament, I could just use the function closest again, passing in 4 as the first argument, and let's say I want them all to be within 10 cents, and I want 10 of them. So these guys are all very close to 400 cents. For more help, there's documentation for all these functions on GitHub. You can just follow this link and it'll take you to the wiki.